everybody, welcome to the second class in the Java for Beyond Beginners free online class by DcodeSTEM. My name is Debeshee and I will be your instructor for this class. In the previous class, we gained an introduction to algorithms and specifically learned two fundamental searching algorithms that help us search for an element in an array in Java, the linear search and the binary search algorithm. Today we are going to explore a very useful class of problems, the problem of sorting an array into increasing or decreasing order. We will learn three specific algorithms or methods to sort an array, and we will examine them to gain an insight on how various algorithms can be used to solve the same problem and how some algorithms might be better than others. But why sort an array? Often, the items stored in an array can be easily ordered. For example, integers can be arranged in increasing or decreasing order. Now, we have seen in the previous class that the binary search algorithm works only for arrays that are sorted. Sorted arrays also make it easy when we want to find the median or the kth largest element and many other functionalities. Finding, accessing, and manipulating sorted data is much easier than unsorted data, especially when there is a large amount of data. That is why people have tried for years to come up with the best possible sorting algorithms. There are many popular sorting algorithms such as bubble sort, selection sort, insertion sort, heap sort, merge sort, quick sort, radix sort, and bucket sort. The first three, bubble sort, selection sort, and insertion sort, are easy to understand, but essentially less efficient than the other more advanced algorithms. But for a small amount of data, they work perfectly well. For today's class, we will do only the first three and leave the rest for the future because they require a more advanced understanding of certain concepts. Let us begin with bubble sort. Bubble sort is the simplest sorting algorithm that works by repeatedly swapping the adjacent elements if they are in the wrong order. Suppose we are trying to sort the array in increasing order. In bubble sort, the largest values keep bubbling up to the end and move to the right position one iteration at a time. We maintain two loops, an outer loop where the index variable I goes from 0 to the last but one element, and an inner loop which goes from 0 to n minus I minus 1. That is, the outer loop reduces the range of the inner loop one iteration at a time. Let us consider the first iteration of the outer loop where I is equal to 0. Now, we must compare each pair of adjacent elements, ARR of j and ARR of j plus 1. If they are not in order, that is, if ARR of j is greater than ARR of j plus 1, we swap them. After moving through all the iterations of the inner loop, we see that at the end, the largest element, 6 in this case, has moved to the last position, which is the right position. Now, in the second iteration of the outer loop, we will check only up till the third last position, at the end of which we will have 5, the second largest element, in the second last position, which is exactly where we want it. Now we continue this process and see that at the end of 4 iterations of the outer loop, which in this case is n minus 1, which is equal to 4, we have a completely sorted array as all the elements have bubbled up to the right position by filling the largest to smallest elements from the right end to the left end. Let us examine the code for bubble sort to get a clearer understanding. The first few lines contain the declaration for the class and the main method. Here we have an unsorted integer array named ARR. The integer variable n stores the length of the array using ARR.length. We now create a nested loop. The outer loop goes from I equal to 0 up to n minus 1, and the inner loop goes from j equal to 0 up to n minus I minus 1, which means that j moves through the range bounded by I, and this range keeps getting smaller and smaller from the right end with each iteration of the outer loop. As the positions keep filling with the correct elements from the right to the left, for each iteration of the inner loop, we compare ARR of j with ARR of j plus 1 and swap them using a temp variable if they are out of order. In this case, out of order means that ARR of j is greater than ARR of j plus 1, since we are trying to sort in an increasing order. If we want to sort in decreasing order, all we need to do is change this sign from greater than to less than. Let us run this code to check if the array is being sorted properly. This is the unsorted array that we have given it. Let's run it. And as we can see, the array comes out in perfectly increasing sorted order. Now let us consider the second sorting algorithm, selection sort. The selection sort algorithm sorts an array by repeatedly finding the minimum element, consider increasing order, from the unsorted part and putting it at the beginning, which has the sorted part. The algorithm maintains two subarrays in a given array. The subarray which is already sorted and the remaining subarray which is unsorted. In every iteration of selection sort, the minimum element from the unsorted array is picked and moved to the sorted subarray. Let us consider this unsorted array of 20, 3, 35, 11 and 2. We must repeatedly find the smallest element in the unsorted subarray. In the first iteration, this is 2. And then place it in the first position by swapping it with whatever is present in the first position. Now, the first element is part of the sorted array, sorted subarray, and the remaining subarray to the right of it is still unsorted. In the second outer loop iteration, we find the next smallest element from among 3, 35, 11 and 20. The smallest is 3, and we swap it with the second position. Coincidentally, it is already in the right position for 3. So now 2 and 3 are part of the sorted subarray, while the remaining subarray to the right of 3 is unsorted. We continue to find the smallest among 35, 11 and 20. Since 11 is the smallest, we swap it with the first position of the unsorted array, that is, we swap it with 35. Now in the last iteration, we must just swap 35 and 20, and we have a completely sorted array in increasing order. Let us take a quick look at the code for selection sort. The first few lines are of course the class and main method declaration. We have the unsorted integer, the same array named ARR, and the int variable n, which has the length of the array. We have two loops nested inside each other. The outer loop reduces the boundary of the unsorted array by moving I from 0 to n minus 1, while j is the inner loop variable which finds the smallest element of the unsorted subarray for each of the iterations of the outer loop. We declare this integer min index, which starts off at I. This is the variable which will make note of the index position of the minimum variable at the end of the complete termination of the inner loop. As soon as the inner loop terminates, we swap the ith element with the smallest found element, which can be accessed using ARR of min index. At the end of all the iterations of the outer loop, each ith variable has been replaced with the appropriate element in the proper order. We just print out the array after that to check if it has been sorted correctly. Let us quickly save this and run this. and we can see that the array is perfectly sorted in increasing order. If you wish to sort the array in decreasing order instead of increasing order, you need to find the largest element in each unsorted subarray instead of the smallest element. This can be done by just changing this sign to a greater than sign instead of the less than sign. And you may even change this variable name from min index into max index, just to make sure that the variable names are intuitively correct, because now you will be finding the number which is the largest instead of the smallest in the unsorted subarray. Now let us move to the third and final sorting algorithm for today, the insertion sort. Insertion sort is a very simple sorting algorithm that works similar to the way you sort playing cards in your hand. The array is virtually split into a sorted and unsorted subarray. Values from the unsorted part are picked one by one and placed in the correct position in the sorted part. Let us consider the simple example array of 23, 1, 10, 5 and 2. We imagine that we are creating a sorted subarray from left to right, one step at a time, for each iteration of the outer loop. In the first pass, 23 remains at 23. It is a sorted subarray of one element. In the second pass, we must place 1 to the left of 23 in this sorted subarray of size 2. So we must move 23 to the right and place 1 on its left. In the third pass, we must make a sorted subarray of size 3 containing 1, 23 and 10 by inserting 10 in the right position. 10 must be inserted between 1 and 23. So 23 is moved to the right and 10 is placed in the correct position. Similarly, in the fourth pass, we must insert 5 in the right place, which is immediately after 1. So 10 and 23 must be shifted to the right. And the last pass inserts 2 in the correct position using a similar procedure. Let us take a look at the code for this, because the implementation of inserting a value in the correct place is not completely straightforward. Here is the code for insertion sort. The first few lines are as usual the class declaration and the main method, the initialization of the array ARR, and the int variable n, which stores the length of the array. As we now know, for each iteration of the outer loop, we must take the ith element and insert it in the correct position in the sorted subarray, which is maintained in the left side of the array. The size of this array increases as I goes from 1 to n. Let us use the int variable key to temporarily store the value of the ith element which we are going to be inserting. Now, to find the correct position to insert this value stored in key, we must move the variable j from I minus 1 to 0 and compare it with this key variable for each iteration of j. As long as the jth element is greater than the ith element, which is now stored in key, we can keep shifting it to the right using the assignment ARR of j plus 1 is equal to ARR of j. At the end of this while loop, which terminates when we encounter a value less than the value in key, we have reached the correct position where the ith value or the key must be inserted. So, we write ARR of j plus 1 is equal to key. We continue to do this till the entire array is sorted. Let us run this program once to check if it sorts the array correctly. This is the given unsorted array, and we now run it. And we have the perfectly sorted array in increasing order. If you wish to sort the array in decreasing order using insertion sort, all you need to do is change this sign here from greater than to lesser than. You may extend all of these sorting programs and integrate them to take user input to initialize the array instead of hard coding it. So basically the user can give you an unsorted array and you can sort it for them and print it out. You can use these algorithms in a variety of other problems where you need sorted arrays for more complex problems where you need to start off with already sorted arrays. With that, we have reached the end of today's class on sorting algorithms in Java for beyond beginners. Feel free to try out these sorting algorithms whenever you need them for more complicated problems. You may also note that Java provides ready-made inbuilt sorting function, and you can of course use them whenever you need to, but it is important to know these basic algorithms because they form the fundamentals of computer science and problem solving. So good luck with using these algorithms whenever you need them. Thank you for attending this free online coding class by DcodeSTEM.